Hello, this is a web presented to the NetSys conference on the one-on workshop. The title is Age of Information in Molecular Communication Channels. The author from the Technical University of Berlin's are Ketki, Lucas, Professor Dresla, and Jorge. We consider a molecular communication system comprised by a source point and a spherical receiver. This source will emit information carried by molecules that will diffuse to the destination randomly, described by a Brownian motion model. When releasing a group of particles, not all of them will reach the destination. Some of them will travel to different directions. Even with line of sight conditions, there will be some uncertainty on the molecular communication process. Accounting for a second undesirable channel effect, the intersymbol interference is markedly strong in molecular communication channels. Considering two consecutive emissions, conditioned by a mechanical interaction of released particle with the medium, some molecules will travel more slower than others, and the superposition of both emissions will be perceived in the receptor. Finally, due to the Brownian motion of the released molecules, it will explore some region when traveling from the source to the destination. As highlighted in this picture, the particle will spend some time around, introducing large delay in the communication process. These three different channel effects are typically addressed independently. They are not jointly analyzed to optimize the communication performance. Instead, here we propose to deal with these three channel effects simultaneously through the age of information concept. The age of information provides metrics concerning the freshness of the received packets at the destination site. It is defined as a linear function of time where the measured time not only accounts for the traveling time of the packet, but also for the time the packet spent on the receiver side before a new packet arrives. Implicitly, the age of information deals with the reception process and the transmission delay here on the channel. Our contribution is to derive the average peak of information on this molecular communication channel. Following several straightforward formulations, we derive this formula for the average peak age of information. The formula is comprised by three terms: a linear relation with symbol time and the propagation delay, and an inverse relation with the packet error probability. When we depict this formula versus the symbol time, then it exhibits the counteracting mechanism between latency and the packet error. The larger the symbol time, the less the impact of intersymbol interference, but the larger the impact of latency. On the other hand, the less the symbol time, the less the impact of latency, but the larger the impact of intersymbol interference. Between both tendencies, there is an optimal point where the peak age of information is minimum, as represented here with the red box. We also validate the theoretical formula with the discrete system provided in this paper, where the channel impact is modeled through a set of coefficients. As exhibit this curve, there is an accurate correspondence between the theoretical formula and the measured average peak age of information. We also illustrate the impact of the propagation distance and the radius of the receiver on the average peak age of information. Following these two curves, the largest reduction of the average PAoI is obtained when increasing the radius than when reducing the distance. Finally, we also summarize some open issues for the further research on this topic. Just to mention, we can consider the impact of mobile environment, that is, when the receiver and the transmitter are not static, and we can also consider the impact of thermodynamic limits on the minimum age of information metric. Energy and information are connected topics. It might be interesting to derive the minimum amount of energy to be expended when achieving a minimum age of information. As concluding remarks, the concept of age of information reveals the counteracting mechanism when implementing an optimally fresh molecular communication system. The resulting trade-off between latency and intersymbol interference derive the optimal solution for the system utilization. This first approach can be further extended to different architectures like multi-hop networks. Thanks for your attention. We are open to further discussion and also collaboration. Here we can have some contact by this mail here on the slides. Thank you.